This paper examines the foundational assumption of homogeneous cosmic time in the FLRW metric and challenges its validity in light of observed time dilation effects and emerging insights from the Buchert formalism. It argues that time dilation, typically seen as a local effect, is indicative of broader spacetime inhomogeneities, which, when aggregated, generate kinematic backreaction and fundamentally alter the average cosmological dynamics. In this framework, time dilation becomes a measurable signature of structure-driven divergence in spacetime evolution. This integration leads to a reframing of cosmic time as a domain-dependent emergent phenomenon shaped by constraint and curvature. In standard cosmological models, the role of time dilation is often overlooked, despite being fundamental to understanding kinematic backreaction. This oversight neglects the nature of backreaction itself, which arises not from exotic components like dark energy, but from the structural inhomogeneities in spacetime. Rather than treating backreaction as negligible, it should be recognized as a structure-driven kinematic phenomenon, one that provides a compelling alternative explanation for the observed cosmic acceleration. In this view, acceleration emerges not from an external dark energy field, but from the desynchronization of time across different regions due to gravitational time dilation. Building on this, the Buchert framework abandons the idea of a single cosmic time, replacing it with domain-dependent temporal resolution. Each region of the universe evolves along its own proper time trajectory, shaped by local geometry and matter distribution. This shift reveals that time is not a uniform backdrop, but a structure-sensitive resolution field that dynamically adapts to coherence patterns across spacetime. Consequently, the cosmological constant may be reinterpreted as an artifact of inhomogeneous averaging, and what we call dark energy may instead reflect our misreading of regionally desynchronized clocks. This aligns with timescape cosmology, which posits that cosmic acceleration is not a real, universal expansion force, but a misperception resulting from comparing asynchronous temporal domains. When time is treated as a structural resolution, rather than a global parameter, the assumption of a universally synchronized clock becomes untenable. The FLRW metric assumes a smooth, homogeneous, and isotropic universe on large scales. This leads to a single universal time coordinate defined by co-moving observers whose clocks are synchronized across the cosmos. However, relativity tells us that time dilation exists, arising from both motion and gravitational potential, which introduces inhomogeneities in the passage of time. Paradox: if time dilation exists, how can cosmic time be globally homogeneous? This paradox invites deeper exploration into the assumptions underlying the FLRW metric and motivates consideration of inhomogeneous models that account for time variation across cosmic structures. Time dilation is not merely a local perturbation, but an indicator of curvature, mass-energy distribution, and structure formation. Galaxies, voids, black holes all create spacetime curvature and thus alter the local rate at which time passes. The existence of time dilation, therefore, points to inhomogeneity, not just spatially but temporally. It challenges the validity of the FLRW assumption that time passes uniformly for all co-moving observers. Time dilation is not merely a local relativistic artifact. In the Buchert timescape framework, it becomes the measurable signature of kinematic backreaction, emerging directly from structural divergence in cosmic expansion. The Buchert formalism provides a framework for dealing with inhomogeneities in cosmology. Rather than smoothing spacetime itself, it averages scalar quantities over spatial hypersurfaces, such as expansion rate, matter density, shear, and spatial curvature. These inhomogeneities, when not ignored, produce a phenomenon known as backreaction, the feedback of local deviations into the overall cosmological dynamics. This feedback effectively alters how the universe expands and evolves at large scales. Backreaction shifts the role of time from a universal backdrop to a regional emergent property. It invites us to model the universe as a set of evolving domains, each with its own trajectory and temporal coherence. This shift reframes backreaction not as a deviation to be corrected, but as an essential driver of temporal and spatial structure, a dynamic interplay where form gives rise to flow. The FLRW model treats curvature as globally averaged, smoothing over regional differences, while the Buchert approach respects regionally evolving curvature that reflects the actual distribution of structure. Inhomogeneity in FLRW is neglected, assumed to be negligible at large scales, whereas in the Buchert model it is central, generating kinematic backreaction that significantly influences cosmological dynamics. In FLRW, time is defined uniformly across all space, based on comoving observers whose clocks tick in synchrony. Time dilation in the FLRW model is omitted from the global treatment, treated instead as a local perturbation, whereas in the Buchert approach, it is essential to understanding how backreaction arises. FLRW does not include backreaction as a significant term. The effects of inhomogeneity are averaged away. Consequently, where FLRW requires a cosmological constant or dark energy to explain the observed acceleration, the Buchert timescape model offers a different explanation, that acceleration may simply emerge from the misinterpretation of clocks ticking at different rates across varying gravitational landscapes. In the Buchert framework, there is no single cosmic time. Each domain evolves along its own proper time trajectory, shaped by its local geometry and matter distribution. The synchronization assumed by FLRW breaks down. Time dilation thus becomes more than a local phenomenon. It becomes a generator of backreaction, altering the global average dynamics. Time is not simply a parameter that ticks evenly throughout space. It is a structure-sensitive resolution field that tracks coherence within and across evolving regions. The cosmological constant, lambda, may be reinterpreted as an emergent term from inhomogeneous averaging. Dark energy may reflect our misinterpretation of clock effects across regions rather than a true universal force. Timescape cosmology, which argues for regional clock desynchronization, aligns naturally with Buchert's view. Apparent cosmic acceleration may thus be an artifact of comparing desynchronized temporal domains rather than evidence of a universal repulsive force. The assumption of a globally synchronized clock becomes untenable when time itself is understood as a structure emerging from constraint. If we understand time as an emergent resolution of constraint across inhomogeneous domains, and we accept that this resolution occurs via nonlinear recursion, we must then ask, what is nonlinear recursion in this cosmological context? Nonlinear recursion is not predictable from the sum of its parts. Outputs feed back into inputs in ways that amplify or dampen effects disproportionately. This implies emergence, where temporal structure or coherence arises not from initial conditions alone, but from feedback loops shaped by geometry, energy density, and constraint. It is a dynamic topology of coherence. Time does not flow, it resolves. Temporal resolution becomes phase-sensitive, recursive, and conditionally stable. When recursive tension fades, when constraint differentials fall below threshold, time itself dissolves. Not in destruction, but in structure. What remains is constraint in potential, a folded stillness awaiting resonance. Thus, time as nonlinear recursion is not forever. It is emergent, contingent, and dissolvable. If it's nonlinear recursion, then it is time. But if recursion halts, time dissolves. When time dilation is treated not as a footnote, but as a formative mechanism, it demands a rethinking of cosmic time. The Buchert formalism provides the tools for such a reframing, where time becomes a recursive resolution of constraint across domains. This reorientation aligns with modern findings in quantum materials science, relativistic field dynamics, and emerging geometric frameworks that treat curvature and constraint as co-generators of temporal coherence. Thus, the universe does not evolve through a uniform time axis. It unfolds through differentiated temporal resolution shaped by its inhomogeneous structure.